Hi, my name is Seungyeon Kim from the University of Illinois. I will be presenting our paper, Disentangling Successor Feature for Coordination in Multi-Agent Reinforcement Learning. Before I begin, I would like to acknowledge co-authors of the paper, Neil van Stralen, Professor Chowdhury, and Professor Tran. I will start with introducing the problem motivations and challenges, provide important background for our work, and explain our approach to the problem. Lastly, I will discuss our benchmark test environments and results. Multi-agent reinforcement learning has shown promising results for solving real-life multi-agent problems, including smart grid controls, robotics operation, etc. One key question that we would like to focus in this paper is how to handle assignment of global reward to ensure coordination among agents. When a global reward is given from the environment to a team of agents, accurately differentiating the contribution from each agent is a challenging problem that would help agents to understand how to coordinate better. Many state-of-the-art methods, such as QMix, achieve this by composing the global value function from individual utility function. Decentralized architectures are a common choice in multi-agent system, where decisions are made locally with minimum communication to other agents. This strategy comes with the benefit of reducing exponentially large state action spaces, and also we can exploit the possibility of sharing a policy among agents to save training and computational wall time. These benefits allow learning control strategy to be more applicable in the real world, but as noted before, reward assignment is a challenge that still needs to be addressed. More specifically, we investigate how to define individual utility function that can be used to train decentralized agents. Our approach is based on three key ideas or contributions. We first use successor feature to separate environment's dynamic from its reward, and second, we use the concept of learnability and factorability to define individual value functions for training agents, which disentangle their contribution to the reward from those of other agents. And three, we implement these ideas in centralized training, decentralized execution architecture, which preserve the benefit of decentralization while stabilizing the value estimation. Before going into the details of our method, I will first introduce the background on successor feature, learnability, and factorability. First, I will introduce the concept of successor feature, which we call SFs. The idea of SFs first came from the successor representation, which was first formalized by Dayan. In the original work, he writes the Q function as a dot product between the likelihood of visiting a state, M, and the reward at that state, R. The formulation is useful because M is agnostic to reward while capturing state transition dynamics. This separation of reward and dynamics serves a key role in our method to distinguish agent-specific reward contribution within a complex multi-agent environment. These variations of the value function formulation still satisfies the Bellman equation. This is why the traditional reinforcement learning algorithm can still be used to learn both M and R. Later, successor features were introduced by Barreto et al., which generalized the successor representation using function approximator, the neural network, and enabled their use in continuous state space. Similar to the successor representation, SFs decompose an environment's dynamic from its reward, where state transitions are captured by the expected discounted future occupancy, psi, of a set of features, phi. A linear weighting, W, then connects these expected features to the value functions and rewards. Next, we would like to introduce the notion of factorness and learnability, first formalized by Toomer. Consider the case when the multi-agent environment returns a global reward. There could be various ways to define private utility functions for achieving this reward. These metrics provide a meaningful evaluations of the quality of those private utility functions. First, factorness is a measure of how well the private utilities is aligned with the global utility. Here we denote the capital G as a global utility, small case g as a private utility, and z as a joint action. Z sub I are the component of z that only depends on agent I, and as a complementary, the z sub minus I is a component of z that depends on all agents other than agents I. The numerator can be interpreted as a counter of how often the gradient of capital G and small case g aligns with respect to the different states. In other words, a high factorness ensures the training individual agents to maximize private utility will simultaneously maximize the global utility. Second, learnability is a measure of how much other agents' action can influence the private utility of a given agent's I. We interpret learnability as a level of noise in the private utility due to other agents. And high learnability implies the private utility reflects the agent-specific contribution, unaffected by the other agent's action. Based on these ideas, Toomer defines the estimated difference utility, they call EDU, as a private utility function that is fully factored and has a high learnability. EDU is based on disentangling or separating the impact of joint actions of other agents from the impact of actions of agents I from the global utility. However, an open question here is how to perform that disentanglement, that is, how to estimate the z sub minus I. We achieve this disentanglement by leveraging the linear decomposition property of SFs. We first introduce a trainable rescaling factor, beta, that re-rates the SF to focus on features that's only relevant to agents I. We then use this factor to filter a set of features, phi I, that corresponds to some reward element, wi, associated with only the agent I. This beta factor is initialized to 1 and limited to be between 0 and 1, indicating this rescaling does not amplify the reward. Assuming the rescaling is done properly, this formulation enables us to redefine the EDU in a SF reinforcement learning scheme, which we call SF-EDU. The next question here is then, how do we learn this beta? We do this by optimizing the learnability of the resulting SF-EDU. Another key idea here is that we formulate a new representation of learnability using SFs that allow us to perform this optimization. This process can be interpreted as filtering out features to minimize noise from other agents, hence maximizing the learnability. Here is overall schematic of our architecture. We adopted a centralized training, decentralized execution paradigm for stability of global value estimation, which affects the stability of EDU estimation. This paradigm is popular because it preserves the benefit of decentralization, such as reduction of the action space or fast training, while providing more accurate centralized feedback during the training, and it allows us to reliably use the global critic within the EDU. It is also applicable in the real-world situation, where the training and development of the policy could occur prior to the execution with aggregated data from all agents. To benchmark our method, we tested on 3 different environments: Predator and Prey, Capture the Flag, and StarCraft 2. I'll focus more on Capture the Flag and StarCraft 2 because we observed most baselines achieve similar performance in Predator and Prey. Capture the Flag is good benchmark cases to test value decomposition, since the reward structure heavily relies on the coordinations of agents, and also the dynamic dramatically changes depending on the territory. The StarCraft multi-agent challenge also provides a wide range of difficulties for testing our method. We compared our results against other state-of-the-art multi-agent reinforcement learning algorithm, including QMix, WQMix, COMA, and Leica. Here we show the result from the CTF environment with heterogeneous agents. We believe QMix and WQMix struggled relatively due to limited exploration in this sparse reward environment. CTF requires searching in the enemy's territory for the flag, which may limit the Q learning method, where exploration needs to be tuned carefully. Here we show the result from StarCraft 2. For the easy map, our method achieves similar performance to most others. We note here that our method took more initial training time, likely due to the initial learning of the successor feature structure. Therefore, the benefit of our method may be reduced for simple environment. However, we really see the performance benefit of our method in harder map. We expect that these performance gains are due to the learning stability provided by optimizing the learnability, which is most beneficial in complex environment. Here is a replay of our policy for the map 27M versus 30M scenario, where we control the 27 red agents. Even without communication, we seem to see the coordinated movement where the agents learn to wait and surround the blue team to win. I conclude the presentation with highlighting our contributions. First, we provided an end-to-end multi-agent reinforcement learning algorithm that has an intrinsic mechanism to handle the scalability of multi-agent system. Second, we introduced the SF-EDU private utility formulation with a training scheme that can optimize the learnability. Last, we demonstrate the benefit of our method in 3 different environments. For future work, we are interested in further simplifying the network structure by utilizing the SF decomposition, which could lower the training cost for larger heterogeneous systems. Also, we would like to include the feasible communication framework to improve the coordination further. This is the end of our slide, and thank you for listening to our presentation.